money. So what you're familiar with, the exponential growth and decay formula looks like this. A is equal to P times E raised to the RT. Again, this was your continuously compounding formula, where P, do you remember what P stood for in this formula when you studied it last year? It was your initial deposit or your initial amount. And of course we had E. R was your interest rate or growth rate. T is time. So basically what we're going to be looking at, the growth and decay formula, is just pretty much a variation of this. This is our general formula for exponential growth and exponential decay. All right, your A of t is the size of a population at any particular time t, so that's what we're solving for. The A sub 0, that's our original population when t is equal to 0, so that is the coefficient of E. K, notice in the exponent is the coefficient of t, that is the constant determined by rate of growth. So what you thought of as the interest rate, we're now going to call that the growth rate. It could also be your decay rate, depending upon whether it's positive or negative. Again, so like I just mentioned, to kind of expand on that, if k is greater than 0, the population grows or increases over time. This is your growth, or your constant rate of growth. If your k value is less than 0, then the population decreases or decays over time. So, for example, if you remember what your exponential growth models look like from last year, remember you have a horizontal asymptote at y equals 0. But if your k value is greater than 0, this is an example of what your exponential growth model will look like. As t is approaching infinity, your growth is approaching infinity as well. Okay? If you take a look at the exponential decay model, again, that occurs when your k value is less than 0. You still have a horizontal asymptote at y equals 0, but it will get small as your t values are approaching infinity. Your A of t is getting closer and closer to 0. All right, so just a visual model as to what's happening when we're looking at these particular problems. All right. So here's an example. So there's really 4 different types of application problems we're going to be taking a look at. So let's take, and you will need your calculator for a lot of these. If you don't already have your calculator out, please take your calculators out. Cell division. It's a process in the growth of many living organisms based on an ideal situation in which no cells die and no byproducts are produced. The number of cells present at a time follows the law of uninhibited growth. Anytime you see that particular phrase, uninhibited growth, they may change the variables, but it's the same type of formula. It's still your A of t is equal to A sub 0 times E raised to the k times t power. Again, so law of uninhibited growth, just another way to say that we're looking at an exponential growth model. N sub 0 is just our initial number of cells. K is our positive constant rate of growth. All right. So let's take a look at an example here. A culture of bacteria obeys the law of uninhibited growth. So again, anytime we're talking about that, we know we're looking at our A of t is equal to A sub 0 times E raised to the kt power. So that's the formula we're going to be dealing with in this particular example. If 300 bacteria are present initially and there are 500 after 1 hour, how many will be present in the same culture after 4 hours? How long until there are 10,000 bacteria? Most of these problems are going to start the same way. If they do not give you that growth rate or the decay rate, that's got to be where you start. You're going to have to solve for the growth rate if they don't give that to you, which they're not giving it to you in this particular problem. But let's pull out what we do know. They're telling me there's 300 bacteria present initially. So what variable does that represent in this formula? That's your what? A sub 0. So I know that there's A sub 0 is equal to 300. They're also telling me that there's 300 bacteria present, 500 after 1 hour. So I know that A of 1 is equal to 500. So like I said, if they do not give you K, which they are not, you have to find K first. So always with the first step, if it's not given, you've got to find your K value, your rate of growth. And what you're going to do is you're going to plug in what you do know into this particular formula to solve for K. So I know that after 1 hour, there are 500 bacteria. So I can take 500, set it equal to, I know that A sub 0 was 300 times E raised to the K times 1 power. Because again, I know after 1 hour, there was 500 bacteria. So I can plug in that 1 for T. So now how am I going to start solving for K? What's going to be my first step? To isolate E to the K, I'm going to have to do what to both sides of the equation? Divide. So I have 5/3 is equal to E to the K. So now what am I going to do to both sides of my equation? I'm going to take the what? Natural log. So natural log of 5/3 is going to be equal to K. Now, this is where I'm going to star this. I'm going to highlight this. You want to store in your calculator. Do not round it to 3 decimal places, because that's not my final answer, is it? I have to use that now to answer some questions. You can get significantly further and further away from what the answer is going to be if you round this at this particular point. All right, so the easiest way to handle this is on your calculators. That store button, remember, is located right above on. Right above on, you see that STO button. So what I can do is I can type in the natural log of 5/3, hit my store button, and just store it in for X. You can store it in for any variable that you want, but obviously the easiest one is the X. So I'll type in natural log of 5 divided by 3, hit my store button, and then I'll hit X. So what that's done now, remember, as I mentioned before, anytime you hit an X on the home screen, the calculator is automatically going to dump in this value. It actually has 100 decimal places in the memory that you're not seeing. So it's automatically going to plug it in for you. So you'll get a much more accurate answer than when if you just rounded it to 3. Because you can get significantly further and further away from what the exact answer is going to be. Okay? Remember, this natural log of 5/3 is an exact value. What you have on your calculators is approximate. Exact is always better than approximations. So any questions on how you store that in the calculator? Always store that K value. Okay? So now let's go ahead and answer the question. So now I know that my model is going to look like this. A of T is equal to 300 times E raised to the natural log of 5/3 times T. So that's the formula now that I'm going to be using to answer the question. All right, so now let's take a look at the first part. How many will be present in the same culture after 4 hours? Well, how do you think you're going to solve this? What are you going to plug in for T? 4. So then A of 4 will be equal to 300 times E raised to the natural log of 5/3 times 4. And remember, we have that natural log of 5/3 stored in the calculator. So when I type this in, I'll have 300 times E. Remember, E is that second ln. And again, it's going to be 4x. If you have, depending upon the model of the calculator, you may have to put parentheses around the 4x to let the calculator know that both the 4 and the x are in the exponent. But with the updated operating systems on 84, you can type the 4x in without parentheses. So we end up with 2,314.845 bacteria. So how much bacteria is present after 4 hours? Okay? So that's part 1. I'll just call that part A. Part B. How long is it until there are 10,000 bacteria? So when they ask me for how long, what variable are we solving for in the equation? We're solving for what? T. So what do you think we're going to do with this equation? We're going to set it equal to what? 10,000. So I'm going to take 10,000, set it equal to 300 times E raised to the natural log of 5/3 times T. So I want to solve for T, so I'm going to have to isolate the base of E. So what's going to be that first step? I'm going to do what? What's going to be my divide by 300. So I'm going to end up with 100 over 3 is equal to E raised to the natural log of 5/3 times T. Remember, t is in an exponent. So now what am I going to have to do to both sides of the equation? I'm going to have to take the what? Natural log. So natural log of 100 over 3 is equal, when I take the natural log of e, I can pull out what's in the exponent. That's going to be the natural log of 5/3 times t. Now what can I do to solve for t? I can do what? Divide by the natural log of what? 5/3. Remember, that's what's stored in the calculator. So now, if you do not have your calculators, remember, this would be exact. That is your exact answer. But the minute you punch it in, again, you can get your approximation. We can do the natural log of 100 divided by 3, and then divided by x. So I end up with about t being equal to approximately 6.86 and the units are hours. So it's going to take approximately 6.864 hours to have that 10,000 bacteria. All right, so any questions on how we're going to be using this equation here? All right, let's take a look at another one. Population growth. The population of a Midwestern city follows exponential law. So again, that exponential law, you're looking at the exponential growth or decay model. So again, A of t is equal to A sub 0 times e raised to the k times p power. Again, we have no idea in this situation whether it's a growth or a decay. So this is calling it exponential law. We won't know until we actually know what the k value is. Again, the population is decreasing, so take a wild guess. If the population is decreasing, is this going to be a growth or a decay? Okay, what can we expect with that k value? That k value is going to end up being what? Less than 0. So it's decreasing from 800,000 to 600,000 from 1998 to 2000. What will the population be in the year 2010? Are they giving you that rate of growth? Are they giving you the k value? No. So just like in the last example, what's the first thing we're going to have to do? We're going to have to find k. Like I said, if they do not give you that growth rate or decay rate, that's got to be your first step. So first of all, with the information given, what is the initial population reading that they're giving me? They're giving me an initial population of what? 800,000. And then from 1998 to 2000, how many years pass when I get the next reading? 2. So then I know that A of 2 is going to be equal to 600,000. Okay? So now I need to plug in what I know into my exponential growth and decay model. So then I know that 600,000 is equal to 800,000 times e raised to the 2k power. K times 2 or 2k. So now what's my first step going to be? I'm going to do what? Divide by 800,000. So when I simplify 600,000 over 800,000, that simplifies to what? 3/4 is equal to e to the 2k. Now what am I going to do to both sides to solve for k? I'm going to have to get k out of that exponent, so I'm going to do what to both sides? Natural log. So natural log of 3/4 is equal to the natural log of e to the 2k. So it gives me the natural log of 3/4 is equal to 2k times natural log of e, and of course natural log of e is just 1. Then what? Divide by 2. So again, I know that k is then equal to the natural log of 3/4 over 2. And what am I going to do with that in terms of my calculator? I'm going to do what? Store it. So again, what happens, guys, is now when I type in that natural log of 3/4, not sine, we don't want sine, natural log of 3 divided by 4, make sure you close that set of parentheses. We're dividing by 2. Hit your store button, which is right above on, x, enter. It overrides the previous value that you had stored in for x. Okay? And notice you do end up with that negative k value. All right, any questions on that, how I found k? Now, the model that I'm going to be using to answer the question, A of t is equal to 800,000 times e raised to the 2 times your, natural log of 3/4 over 2 times t. That's the model we're going to be using. Again, that natural log of 3/4 over 2 is what's stored in the calculator. But that's the formula we're now going to be using to answer the questions. So now, what will the population be in the year 2010? Well, from your initial reading of the population to 2010, how many years have passed? 12. So really what I want to find is I want to find A of 12. So I want to plug 12 in for T. So then my A of 12 will be equal to 800,000 times E to that K value, which I've stored in the calculator, times 12. So I just circled that K value here, so I just have to rewrite that natural log of 3/4 over 2. I circle that because that just reminds me of what's stored in my calculator, that's all. All right? Or you could write it all out. 800,000 times your E raised to the 12 times X. So we end up with approximately 142,382.813. Is that really a realistic number? No, because we can't have 0.8 of a person, can we? So realistically, in the year 2010, what is the population going to be? 142,382. We would not round that up because it's not reaching that 383rd person during that year. Yes?
Decreasing, so you would round it up? Since you're going down, you haven't reached like the smaller number yet, right?
Oh, you're right. Yeah, you're right. So it would be 142,383. Yeah, good point. You're decreasing. You're absolutely right. But actually in calculus, this is where you biology people and science people are going to go crazy. You would get points off. Unless they tell you to round to the nearest whole number, you must round it to 3 decimal places. So they would take off if you actually rounded it. Even though it's 0.8 of a person, they would take off if you actually rounded it. Unless it specifically in the direction says to round to the nearest whole number, you must always round to 3 decimal places, even if you're dealing with a 0.8 of a person. So, yep, they will take off. Okay? So any other questions on that one? All right. Radioactive decay. Still following the same model, that A sub 0 times E to the KT. And again, we're talking about decay, so we know the K value is going to be less than 0. Again, this happens a lot when you're dealing with nuclear power plants. Unfortunately, we know that there's been nuclear accidents. The problem is when we're talking about a radioactive material that's released into the air, a lot of times scientists do not know what that initial amount of radioactive material that was actually released into the air. So they have no idea what that initial amount of radioactive material that's been released. So this is where you have a little bit of a twist to your exponential growth and decay model. We're still using that A sub 0 times E raised to the K times T power. That A sub 0 still represents the initial amount. And K is still your constant rate of decay. So radioactive iodine is a byproduct of some nuclear reactors. Its half-life is 60 days. So we talk about half-life, and this is when we do not know what that initial amount is. This is when we're going to have to use that half-life to help us establish the K value. So what that means is after 60 days, half of the original amount will be left. So that's what scientists know about a lot of this radioactive material. They'll know how long it takes to decay down to a certain amount. So unfortunately, suppose a contained nuclear accident occurs and gives off an initial amount of C of radioactive iodine. Write an equation for the amount of radioactive iodine present at any time t following the accident. So just like we've been doing, they had not given you that rate of decay. So before you can write the equation, you always have to find K. The issue here is that in order to do that, to write our equation A of t is equal to A sub 0 times E raised to the KT power, we do not know what that initial amount is. That makes this problem a little different. So again, let's talk about A sub 0. I know when I'll have half of A sub 0, don't I? When will I have half of A sub 0? I'll have half of A sub 0 after how many days? 60 days. So I know half of A sub 0 will exist after 60 days. Does that make sense to everybody? So I can use this information now, just like if I knew, like, you know, after 60 days there were 20,000 grams of this radioactive material. I'm going to take 1/2 A sub 0, set it equal to A sub 0 times E raised to the 60 times K power. Well, first of all, you're not solving for A sub 0, so it's okay to divide out that A sub 0. So I'm left with 1/2 is equal to E raised to the 60K power. So now how do you solve for K? What are you going to do to both sides? You're going to take the what? Natural log. So natural log of 1/2 is equal to the natural log of E to the 60K. So that means natural log of 1/2 is equal to 60K. Now to solve for K, what am I going to do? I'm going to divide by 60. So there's your K value. So part A just wants us to write the equation. So to write the equation, I'm just going to plug in this K value into my formula. So A of T is equal to A sub 0 times E raised to the natural log of 1/2 over 60 times T. So let's look at part B. How long, so what am I solving for when it asks me for how long? T. Will it take for the radioactive iodine to decay to a level of 20% of the original amount? So what are your thoughts? What are we going to have to set this equation equal to? We're going to set it equal to what? I want 20% of the original amount. So, yeah, 1/5 of A sub 0, 0.2. A sub 0 is equal to A sub 0 times E raised to that K value times T. And again, what can I divide out of both sides of the equation? I can divide out the what? A sub 0. And again, instead of writing that K value over and over again, I'm just putting that K with a circle. To remind me, I'm going to store that in the calculator, which I need to do. So let me store the K value first. So let's see, natural log 0.5 divided by 60, and then store for X. And notice you do get that negative K value. Now, what are you going to do to both sides of the equation to solve for T? You're going to do what? What are we going to do to both sides? We're going to do what? Natural log. And I know when I take natural log of E to the KT, that's just going to leave me with KT. And then I can do what? I can divide both sides by K. So natural log of 0.2 divided by that K value gives me approximately 139.316 days. So any questions on the half-life problem? So like I said, a lot of times scientists will not know what that initial amount, but they will know the half-life of a certain radioactive material. All right, so any questions on that one? All right, another type of exponential growth and decay is called Newton's law of cooling. The temperature of a heated object decreases exponentially over time towards the temperature of a surrounding medium. This could also be used on the flip side. If you take something out of the freezer and you want to, or I'm thinking of what? If you take a cake out of the oven, you're taking it out of a 400-degree oven. Well, obviously, when you take it out of the oven that's 400 degrees, you want to cool it off. What's happening with the temperature of the cake? It's decreasing, isn't it? So you can do it. You can take something out of the freezer, heat it up, or you can take something out of the oven and cool it down. It can be used either way. They call it Newton's law of cooling, but it can be used to actually heat the object up as well if it comes out of the freezer. U of T is your temperature of an object at time T. The uppercase T in this formula is the temperature of your surrounding medium. Typically, this is your room temperature or temperature of wherever the object has been placed. U sub 0 is your initial temperature. K is your rate of cooling. And T is time. So again, those are your different variables that are represented in the formula. Okay? So let's take a look. A frozen steak has a temperature of 28 degrees. It's placed in a room with a constant temperature of 75 degrees. After 10 minutes, the temperature of the steak has risen to 35 degrees. Just like we did in all the other examples, they're not giving you a significant piece of information. They're not giving you what? The K value. So like in all the other problems, your first step is you have to find K. If they do not give you that rate of cooling or rate of growth or rate of K, that's always got to be your first step. So let's talk about what they are giving me. The uppercase T. What is the room temperature or the temperature of the surrounding medium? The room temperature is what? 75 degrees. So they're giving me that. Let's see. What is my U sub 0, the initial temperature of the object? What's the temperature of that steak when they took it out of the freezer? 28 degrees Fahrenheit. Let's see. They're not giving me K. That's what I'm solving for. And they tell me after 10 minutes, the temperature has risen to 35 degrees Fahrenheit. So they're telling me that U of 10 is equal to 35 degrees. So just like I did with all the other problems, I'm going to plug the variables into this particular formula, and I'm going to solve for K. So again, my U of T was my 35 degrees is equal to my upper, let's see, the 75 degrees plus my initial temperature of 28 degrees minus 75 degrees times e to the K times 10. What's going to be your first step? Subtract the 75. So negative 40 degrees. And what's 28 minus 75? 28 minus 75 is going to give me, let me go ahead and subtract that, negative 47 degrees, e to the 10k. Then what? Divide by negative 47. So I have 40 over 47 is equal to e to the 10k. And then our favorite, what are we going to do to both sides of the equation? We're going to take the what? Natural log. So I know natural log of e is 1. That leaves me with a 10k on the right. And then finally, what am I going to do? I'm going to divide by 10. And again, what are we going to do with that k value? Just like in the other problems, we're going to do what? Store it. So now I can go ahead and start answering the questions. What will the temperature of the steak be after 30 minutes? So I want to find A of 30. So I know A of 30 is going to be equal to, again, in my formula, again, we're looking at, again, my room temperature, which was 75 degrees, plus your 28 degrees minus 75 degrees times e raised to the 30 times k. So pretty straightforward, just going to plug and chug. Don't have to worry about doing log of any side of the equations. So after 30 minutes, A of 30 is going to be approximately equal to 46.030 degrees, or 028, excuse me. And you quite always round to 3 decimal places. Okay? Do so? Are we okay on that? All right, now let's look at part B. How long, so when they ask you for how long, what variable are we solving for? We're solving for what? T. Will it take to thaw the steak to a temperature of 45 degrees? So I'm going to take my formula, I'm going to set it equal to 45 degrees. So 45 degrees is equal to 75 degrees plus the 28 degrees minus 75 degrees times E raised to the K times T power. Again, K is what's stored in the calculator. So my first step is going to be to subtract the what? Subtract the 75, so it's going to be negative 30 degrees. 28 minus 75 I know is negative 47 degrees times E raised to the KT power. Divide by negative 47. So 30 over 47 is equal to E to the KT. Then what am I going to do to both sides? I'm going to take the what? Natural log. Which leaves me with just KT, and then divide by K. So it's going to take me approximately 27.839, what's my units? Minutes. For the steak to reach a temperature of 45 degrees. So again, it's just another application. I will give you guys, by the way, on the test, I will give you the Newton's Law of Cooling formula. So I will give you this here. You just have to know what pieces the variables represent. Again, I do expect you to know that A sub 0 times E to the KT. You'll be doing that enough that you should know it anyway. You won't get that A sub 0 times E, but you will get this one. I'm not going to tell you what T is or what U sub 0 is, as long as you know that. Okay? So any questions about using the Newton's Law of Cooling formula? Go down. All right, last type of thing. So, a logistic model. So, a different kind of function you haven't studied before is called a logistic model. And a logistic model has a lot of the same characteristics as an exponential function. However, what happens, instead of the end behavior of the exponential model going to infinity, it will eventually level off. So this is an application of, let's say, population growth or sales of a product. We all know what happens when a new iPhone comes out. Sales go up. But eventually, what happens with the sales? They're going to do what? They may go up a little bit, but eventually the sales are going to level off. So it resembles a lot of an exponential model, but then what happens is it eventually levels off. So you still typically have your horizontal asymptote at y equals 0. So as it approaches infinity, it's still increasing, but then it levels off. So what ends up happening is you have two horizontal asymptotes. All right? Or it could be decaying. Oh. It levels off both ways. I did a bad job drawing that. But it levels off at the top, and then it starts to decrease. Okay? This numerator is a very significant number. When you have your formula, this is what the model looks like for logistics. C is what's called your carrying capacity. And in the graph, that is your horizontal asymptote. So for example, if you've got a lake, the lake is only so big, and you have a population of fish. Eventually what happens, you can only have so many fish that live in a lake, because what happens, they run out of space, and they can run out of what? Food. So the carrying capacity is how many fish would that lake sustain? What's the total possible number of fish that lake could have? So let's take a look at this one. So here's an example of bald eagles. So 6 American bald eagles are captured, they're transported to Montana, and they're set free. Based on the experiment, the environments expect the population to grow according to the model. So again, looking at this numerator, right away, in this environment, how many bald eagles can be living in this environment? 500. That's actually your answer to part B. So part B, the carrying capacity is 500 bald eagles. When you go to graph a logistic model in the calculator, you're going to have to adjust your viewing window. You've got to make sure your Y max is a little bit larger than whatever your carrying capacity is. So when I go to graph this on my calculator for part A, 500 divided by, make sure you put parentheses around that denominator, 1 plus 83.33 times e raised to the negative 0.162x. So when you go to your viewing window, it only plugs in the value on the home screen. It will still recognize x as your independent variable in graphing. The only time the calculator dumps in that x value is when you're on the home screen. I need to clear out what was under my y2 as well. So when I go to my window, right now I have my x min set to negative 10, my x max to 20. That's just from a previous example that I did, so I'll leave it alone. But my y max is only going up to 10. Well, I know where's that horizontal asymptote on this graph going to be. That horizontal asymptote is going to have to be up there at what? 500. So I'm going to set this to maybe 525 to make it a little bit bigger and hit graph. You want to be able to see that horizontal asymptote. You may have to adjust your x max. My x max is going to go out to 20. So I'm going to obviously have to adjust out my x max because I can't see that horizontal asymptote. I'm going to make my x max 75. So now you can see how it does resemble a lot of a exponential growth, but then notice it levels off. So that's what a logistic graph looks like. All right? So again, what we know is that up here at 500, as my graph goes up, it's going to level off as I get closer and closer to 500. Okay? So now let's see. I already answered part B. The carrying capacity is 500. What is the predicted population of the American bald eagle in 20 years? So what I want to find is I want to find P of 20. So all I'm going to do is plug in 20 for T. So 500 over 1 plus 83.33 times e to the negative 0.162 times 20. Now you already have this loaded in your calculator. You already have it graphed. You want to type this in on your home screen, be by guest. But just go to your table of values, second table. You can change your table set. Right now it's defaulted to auto. If you change that independent from auto to ask, so under second window you'll see this menu. Now don't freak out. What's going to happen when you go to your table of values, there's nothing there. So it's waiting for you to type in an x value. So I can type in 20 under x and hit enter. You've never known that. See, it's amazing.
Wait, that is so much.
So if you want to do a decimal, you want to do a fraction, you can now do it. But now the problem is you guys are going to freak out because you may go to your science class and you're going to forget. You look at your table for something and the table's gone. So don't forget to change it back to auto. So how many bald eagles are there going to be after 20 years? Approximately what? 117 bald eagles. I didn't invent the calculator. I just discover these things too. Typically, it's you guys that find stuff and you show me over the years. All right? Trust me, I do not know everything there is to know about this calculator. All right? So are we good on part C? Part D. When will the population be 300? So what variable are they asking me to solve for here? T. So again, I want to know when 300 will be equal to 500 over 1 plus 83.33 times e to the negative 0.162 times t. Obviously, do not solve this by hand. Use your calculator. You already have the logistic equation loaded in your calculator. So what do you think you can set under y2? You can set what? 300. Just type your 300 under y1 or this one under y2. And then find your point of intersection. All right, so don't waste your time and solve it by hand. You can if you want to, but I don't know why you'd want to. So then when I hit graph, I can now find the point of intersection by going under second trace, option 5 intersect. So at about 29.804, and my units are years. So 29.804 years for that population to reach 300. Okay? Any questions about what a logistic model is? All right?